Welcome back, folks. I wanted to work one problem and do some simulation with it because a lot of these problems come out of textbooks, or even worse, they come out of my brain. And I think we lose sight to the fact that these are signals that we can measure, that I can put an oscilloscope on. And since I don't have an oscilloscope, well, I do have an oscilloscope. I don't have any of the components. I don't have a signal generator, things like that. Since I don't have all of the equipment I need, we're going to do this in simulation, but I want you to see the time domain signal go into the circuit and come out of the circuit and match the analysis that we do. So I have a problem. We're going to do the analysis using phasors the way we have. And then I have the simulation. I made the simulation and using LTSpice, which I think is what we're using for labs. You know by now, but I just got off the phone with somebody who gave me maybe a better alternative, so I got to go. I've got a week. I can totally rewrite all my labs. Okay, anyhow, let's do some phasor analysis. And then let's see that the simulated results match in a reasonable way. So we've got Vs, and we're given a voltage for Vs, and we want to find V out over here. The first thing I do when I look at this circuit, if I'm being a purist, I would say leave it just the way it is. But hey, look, these two inductors are in series, and since they're in series, I can just add them. Okay, so that's a 3 and a 6, and that's not an eraser. There's an eraser. So I can combine those and simplify my analysis just a little bit. Okay, and we get 9 henries for that one. Beyond that, I'm going to do mesh analysis like I've been doing. Okay, so I1 and I2. No current supply, so it's all KVLs. I can't quite do the shortcut here. Well, I got to move to the phasor domain. That's what I get when I take phone calls in the middle of lecturing. I've got to move to the phasor domain first. Let's go ahead and do that. Omega is 40. That's an omega. 40 radians per second. And let's call this L1, and let's call this L2, and let's call this R1 and R2, just so that we can be clear on what we're talking about. So the impedance of L1 is then J omega L1. Okay, so we get J40 times 8. So that looks like it's going to be J 320 ohms to me. ZL2 is going to be J omega L2, also known as J40 times 9 henries. Okay, which is going to be J 360 ohms. Okay, so we've moved to the phasor domain for those two, J360, nope, J320 and J360. Okay, this is 50 ohms, and this is of course 400 ohms, and this is 25 at an angle of 45 degrees, and that's in volts. Yeah, I can do the shortcut. As long as I'm in the phasor domain. Almost duffed that one. You should see how many outtake videos I have. I really try to do these in one take, but maybe I'll clip those together for you. End of the semester present to watch me fumble and cuss a lot. Okay. What does I1 touch? These are both KVLs. What does I1 touch? It touches J320 and the 400. So up here I get positive 400 plus J320. What does I1 share with I2? It shares the 400. So it's going to be negative 400. Okay. And then this is negative 400. And then what does I2 touch? It touches 450. 450 plus J360. Not degrees, ohms. Okay, we're going to invert that, and we're going to multiply it by the sources on each mesh, And there's only one of them. It's over here, and this is going to be 25 at an angle of 45 degrees. Okay, and there's no source on the second one. That's going to give us I1 and I2. I'll slide to the right in a moment. And let's figure out what that is. So grab your calculators, pause the video, get the right answer. Okay, there's the answer I got. Hopefully you got something similar. 47.5 at an angle of negative 24.6 degrees, and that's milliamps. 33 milliamps at an angle of negative 63.3 milliamps. I'm going to go ahead and store that. I got my calculator here. And let's go back and look at the original circuit. We need V out, right? So V out is going to be I1 minus I2. Those are the currents that touch the resistor, and the polarities match the passive sign convention according to the polarity labeled on the original schematic. And we're going to multiply it by 400 since that's the resistance. So I stored those. Let's go ahead. I think I can do that one live and quickly. Times 400. And from that I get 11.98, pretty much 12, at an angle of 18.8 degrees. And that's in volts. Okay, that is our phasor solution. We can get a time domain solution by using the inverse phasor transform. 11.98 cosine 40t plus 18.8 degrees in volts. And that's the right answer, but it's really easy to kind of lose sight of the fact that, hey, that represents something in the circuit. So what I would like to do now, let's mark that. Use the stars to mark that. What I'd like to do now is simulate that. So I'm going to take this circuit and I'm going to put it into LTSpice. I already put it into LTSpice. And it looks like that. Okay. So if we're using LTSpice, you're comfortable with this. If we're not using LTSpice, it works the same as the other thing that I chose. We'll see. All right, so I've got all of the components. I even broke those out into a 6 and a 3 because it honestly doesn't matter. It's going to simulate the same way. And I set up this waveform. LTSpice only has sines. It doesn't have cosines. So we're going to have to pay a little bit of attention to the phase, and we'll get by. It's correct. I've already checked it. Okay, but we set up all of this stuff. So it's a sine. There's no DC offset. It's got an amplitude of 25, right? The original source is 25 at an angle of 45. I didn't bother to put in a phase angle, and I'll explain that in a moment. But the frequency here, instead of 40 radians per second, I had to enter it in hertz, right? So take 40 and divide it by 2 pi, and you get 6.3662. I was pretty accurate on that, as accurate as it would let me be. And then I ran it for 1,000 cycles. That was enough time for the inductors to charge and leave their transient state. And we haven't talked about transients yet, but that's what's coming after phasors. So I needed the inductors to charge up all the way so it reached a new steady state. Okay, so I ran that and I got these waveforms down here, and look, the transient's happening here, and we need to figure out this phenomena. It doesn't quite line up with the way the results should be early on because the inductors have an initial condition and it needs to overcome that initial condition. So rather than look there, I looked over here. I grabbed a little slice over here out at 18 seconds, like way far out, probably enough time to have actually charged the inductors the correct way. So, and I got these waveforms. So the first things, you know what, let's grab a slice here. Let's grab, like I said, let's grab a out here around 18 seconds. Come on. Come on, screen capture program. Did it crash? No, there it is. Apparently, my screen capture program shares a button with LTSpice. Hold on, folks. All right. Little foibles. There we go. There's our output. Okay. Our input is in green here. So this is VS, right, was 25 at an angle of 45 degrees. Okay. And our, is that right? Yep, 25 at an angle of 45. And our V out was 11.98, whoops, degrees, 11.98 at an angle of 18.8 degrees. Okay, so the first thing we want to notice is the magnitude. Okay, so we want to make sure we have a magnitude of a phasor, slightly different blue, that's right around 12. And we'll go back and look at the LTSpice because I can throw a cursor down there. And we want to make sure that we have that plotted correctly so that it has a magnitude of 25, just like we practiced when I was introducing phasors. Okay, so let's go look at LTSpice. And looking at that plot, yeah, that looks like it's right around 25, and this one looks like it's right around 12. And if you squint real hard, it looks like it's just below 11. Okay, so I'm pretty comfortable to say that this is 25 volts, and that this is 11.98 volts. Okay, that's the first thing we got to think about. The next thing we have to think about is the phase angle. Okay, and we know how to read phase angle off of time domain plots, and we just need to do that here. So let me flip back to LTSpice, and how do I get my cursor? Where'd it go? This is what happens when you use one too many programs. Hold on. Well, like I said, you've been using it now for a few weeks, and I'm dusting off some cobwebs because I haven't done the labs yet. That's coming. Hopefully it all looks seamless to you, right? Okay, so click up here and we can grab our cursor, and that ends up being right 24.98. So we don't have a data point exactly on it, but it's pretty stinking close, right? And then we can click on the blue over here and play the same game, and that's at the best we got there is 11.85. Okay, not great, but there is some rounding, and we're not necessarily hitting that exact peak because we have discrete points we've gotten out of the simulation. So enough to make me feel comfortable. Okay, so let's put this on the peak here, and it looks like we've got 18.417, let's call it, seconds. So we got 18.417 seconds for the green. And then let's play the same game for the blue. I'm looking for the positive peak, and it's just shifted to the right a little bit, 18.428. Okay, 18.428 seconds. Maybe I need some more precision in there, but I think with all of our rounding error, this is going to be a close result, but it's not going to be a perfect result. Okay, so delta t in this case is negative, what is that? Negative 11 milliseconds. Okay, and we can convert that to a phase difference by saying, okay, delta t is in seconds. Oops. And I want to divide by the period, and I want to multiply by 360, right? And that's going to get me back to the phase angle. Okay, so I need to know the period. I don't have the period. T equals, I have omega, and if I divide by 2 pi, that's going to get me frequency. Wait a second, that's backwards. T equals 2 pi over omega. Okay, so 2 pi divided by 40 radians per second is going to give me a period of 157 milliseconds. Okay, so if I take negative 11 milliseconds and I divide by 157 milliseconds, and then I multiply by 360, I get negative 25.2 degrees. Now, wait a second, that doesn't match 18. I call shenanigans, right? But if I take 14 and I subtract, if I take 45, right, up here, and I subtract 25.2, I get 19.8. Ooh, I'm off by a degree. I'm going to chalk that up to a little bit of error in reading my plot. Okay, so putting that all together, we say 45 degrees minus 25.2 degrees, because that's the shift from the blue, that's the shift of the blue from the green, is equal to 19.8 degrees. And because of my plot reading skills and some discretization, because it's a digital simulation, we're going to say that's pretty close. It's a degree off to 18.8 degrees. Okay, so this is what I would get out of an oscilloscope, and I would have to take these measurements and do the similar kind of thing to validate the phasor analysis. But if we do it, we build the circuit correctly, we measure it correctly, we read our values as close as we possibly can, then we end up with a simulated result that matches our calculated result. And that gives me a little bit of confidence that I did this all correctly. The only thing I could do that would give me more confidence, prototype it. Okay, you got to build it, you got to measure it, and you got to see that it matches all of this stuff. All right, I hope this helps put it all together for you. We're moving on. We got to figure out what's happening when we first turn on the circuit. And that's what we call a transient state of the circuit. And we're going to figure out how to do some simple transient analysis in this class. Stay tuned and good luck.